So, good morning guys. I'm Eliezer Kailing Piscos from BSME 2CM3. So, in today's video, we will tackle about the Breton cycle. So, what is Breton cycle? So, Breton cycle is a gas power cycle by George Breton in 1870. So, for its diagram, Breton cycle consists of a compressor, heat exchanger, turbine, and other heat exchanger. So where do we use this cycle in our real world? So the common applications for these cycles are the gas power plants and aircrafts. So in dealing Breton cycle, we can assume that our working fluid is air modeled as an ideal gas. So air will enter the compressor. Through compression, the air molecules get squeezed, increasing its pressure and temperature. On this process, we need to increase the pressure and temperature to sustain combustion. So while assuming that there is no change in entropy. So how to solve the work of compressor? So we can get the work by using the control volume energy rate balance equation. So work time rate of change of the energy contained within the control volume at the time t is equal to net rate at which energy is being transferred by heat transfer at time t. So minus net rate at which energy is being transferred by work at time t plus change in enthalpy plus change in kinetic energy plus change in potential energy. So now let's move on to the next component in which in which is the exchanger or the combustion chamber. So a fuel will be injected here which will mix to the pressurized air molecules with the help of an igniter. So a combustion will take place. This will further heat up the molecules, thereby increasing its temperature and increases its enthalpy. So in this process, we assume that the process is constant, that no pressure drops happen in its flow. Now, to solve for the heat addition of a control volume heat exchanger at steady state, we can assume that we just use some of the equations and assumptions that we have used on the compressor. So our next component is a turbine. So it's a turbine or turbine. So after the heat exchanger, our heated and energized air fuel mixture will enter and rotate the turbine. So this turbine will rotate the compressor as they are in one same shaft. So this air fuel mixture will also exit the turbine in a high velocity, which will provide thrust to the aircraft. So, and as you might notice, this is the applications of Newton's third law of motions, which states that for every action there is an equal and opposite reaction. So in this process, just like what we did in compressor, so a steady state control volume turbine will have no mass accumulation within a control volume, and the time rate of change of the energy contained within the control volume at time t is 0. So entropy is constant. There is no heat transfer to the surroundings. Potential and kinetic energy effects are neglected. But in contrast, with a compressor, turbine expands the gas, which increases its volume and decreases its pressure. So in addition, turbine generates work. So our work here is a positive. So our final equation for the work output is equals to M times H3 minus H4. So finally, for the last component is the second heat exchanger. So for jet engines, heat exchanger is just the surroundings. So that is the reason why the heat exchanger and its flow path is drawn as dashed lines or imaginary lines. So on this component, the working fluid is being exposed to the ambient air. So by the second law of thermodynamics, this working fluid will transfer its heat to the surroundings. So as it is higher energy value than on the air molecules on the surroundings, and so this means that the heat is rejected here. So now to solve for the heat rejection, we just assume that the things we have assumed on combustion chamber, except for the fact that our heat here is a positive one. So our heat rejection is Q out is equals to M times H4 minus H1. So that's all, and thank you for watching. I hope you've learned something. So bye.